Now let's talk about Eulerian circuits or Euler circuits. An Euler circuit is a circuit, so it starts where it ends and it doesn't repeat edges, but to make it an Euler circuit, it must visit every single vertex and edge in the graph. So in the Königsberg bridge problem originally, we were looking for something similar actually. We were looking for what's called an Eulerian path, which visits every single edge and vertex, but it doesn't need to end where it started. So let me think about Eulerian circuits and when they exist. To do that, let's just get an example of a graph that I think has an Eulerian circuit. And we'll notice something about it. So in this graph, I can start anywhere and travel each of the edges exactly once and visit all of the vertices. So starting and ending at the middle. I mean, I can do that starting at a different vertex just for variety here. I could start over here. Not ever repeating edges. And visit each vertex and start and end at the same place. So this graph has an Euler circuit. Let me notice something about the degrees of the vertices. The degrees of most of the vertices are 2, and the middle one is 4. Those are all even numbers, right? And if you think about it, this is what theorem 10.2.2 says, if a graph has an Euler circuit, then every single vertex must have even degree. Why is this the case? Well, if you have an Euler circuit, then every single vertex is visited by that circuit. What that means is there must be at least one edge incident at every vertex, right? And of course, anytime you enter a vertex, you must exit that vertex, right? So what that means is the degree of the vertex is forced to be even because the number of entrances has to equal the number of exits. And remember, since we're talking about an Euler circuit, edges aren't repeated. So the entrances and the exits are distinct, and there are exactly as many entrances as exits. And that includes the initial vertex that you start at. You leave, you may revisit that vertex several times, and then you finally enter that vertex one last time in the end. Okay, so there you have it. This is a nice way to check quickly to see if a graph doesn't have an Euler circuit. So for example, if I know that an Euler circuit exists, then every single vertex must have even degree. That's what I've just argued. So if I notice that any vertex has odd degree, then there's no way that there is an Euler circuit. In particular, remember the Königsberg bridge diagram looks like this. So this was a really bad situation because many of the vertices had odd degree. And if you have at least one that has odd degree, then there is definitely not an Eulerian circuit. What's even more interesting and a bit harder to show is that as long as your graph is connected and every single vertex has even degree, you're guaranteed to have an Euler circuit. So the book lays out a proof, and there's a distinct proof involving a completely different algorithm. Let me go ahead and present the algorithm that's called Flurries Algorithm, just as an alternative to something that's presented in the book. So I'm going to present Flurries algorithm, and this is an algorithm that produces an Euler circuit anytime you have a connected graph whose vertices are all even. It uses the notion of a bridge, so let me explain what a bridge is quickly. Okay, so in this graph right here, let me notice some things about some of the edges. This edge right here has the property that when you delete it, the graph becomes disconnected, right? So that right there is called a bridge. And there's some other bridges. Look at this one right here. If you erase that bridge, again, the graph becomes disconnected. You got a piece right there and a piece right there. So any edge whose removal produces a disconnected graph is called a bridge. And these edges over here are not bridges. because you can remove them without disconnecting the graph. Okay, so Flurry's algorithm goes like this. Start at any vertex in the graph. When you're constructing the circuit, you sort of like write it down, and then you are going to cross any edge that's not a bridge. So at the beginning, you're guaranteed to have some non-bridge edge. That takes a little bit of argument using, you could use like the degrees of the vertices in the overall graph. I'm going to skip the justification right now just so I can explain the algorithm, and we'll run through a few examples. Okay, so start at any vertex, cross any edge that is not a bridge, and now you're at a new vertex. And you're basically going to keep crossing edges and sort of writing them down as you do so. And at any time, you're going to decide on crossing the next edge. Okay, so that's it. You traverse the vertices of the graph one by one, actually the edges of the graph one by one, and you're just crossing the edges that are not bridges first. When you're forced into crossing a bridge, you do so, but it's going to be necessary that if you're in that situation, the bridge actually is a bridge between an isolated vertex and the rest of the graph. So let's go through an example so that you can see how this works. Okay, so again, this is an alternative to the algorithm that's presented in the book. So let's take a look at this graph right here. The theorem says that as long as the degrees of each of these vertices is even, and the graph is connected, which it is, then we're guaranteed to have an Euler circuit. And you can see here I've got degree 4, 4, 4, 2, and 2, and the graph is connected, so there should be an Eulerian circuit. I'm going to go ahead and write one down using Flurries algorithm. So whatever, let's just start over here at V3. Let's choose to cross an edge that's not a bridge. All right, well, neither of these edges are bridges, so I'm going to go ahead and cross E4, let's say. And that brings me over to V2. And I'm going to erase that bridge. Erase, I'll just scribble out like that. Now I'm at V2, and I've got 3 edges left, 1, 2, and 3. None of them are bridges, so I'll go ahead and cross E1, let's say. Write it down and delete it. Okay, and now I'm at V1. As you can see here, V1 now has only another edge connected to it, and that then is a bridge edge, because if you remove edge 8, V1 is dangling, and then the rest of the graph left over is here. So E8 disconnects what I have left of the graph. So, okay, that's a lot. I'm forced into erasing that bridge. Wrote this wrong. So I go ahead and do it, write it down, and now V1 is out of the graph as well. I erase V1. All right, I'm at V4. These 3 edges are not bridges, so I can cross whichever I like. How about E7? And that brings me to V5. V5 has 3 edges attached, none of which are bridges, so let's cross E2, bringing me to V2. And then at this point, there's only one edge left connected at V2, which is edge 3. That's a bridge. Deleting E3 leaves V2 isolated, and the rest of the graph is sitting there. So I'll go ahead and cross E3 and delete V2. Okay, I'm at V5. There's a bridge, which is E6. Brings me back to V4, the bridge E5, and I'm back to V3. So this right here is an Euler circuit through the graph. Maybe I will sort of run through that again and use a white marker to make it look like I'm erasing as I go. So I start at V3, erase E4, make it to V2, erase E1, make it to V1, erase E8, that's the first bridge. E7 goes, then E2, then E3, erasing V2. I'm at V5 and I cross E6, which is a bridge at this point. Erase that, then E5, and finally to E3. So that's a visual of going through the algorithm to create this Euler circuit. All right, let's do another one. Before I start trying to run through the algorithm, what do we notice about this graph? It's got a bunch of odd degree vertices, right? This vertex has degree 3, this down here has degree 3, this one has degree 5, this one has no Eulerian circuit. So don't even try. It's connected, but it's got at least one odd degree vertex, so that's no good. All right, what about these graphs down here? Looks like this one has all even degree vertices. I think I'm going to try and find the circuit. So let's just start somewhere. How about A? I'll write that down. The edges aren't labeled, so I'm just going to write the vertices as I cross them, or encounter them. So I'm going to go from A to B. Both of those edges were non-bridges, so I have the choice there. So now I'm at B. Actually, none of these edges are bridges, so I can cross whichever I like. How about this one? So now I'm here at I. I do not want to cross this bridge, right? Because I've got some non-bridge options, and the algorithm says to choose a non-bridge if you can. So I'm going to choose, I guess, going down to F. And now there are no bridges attached to F, so I can just choose whichever I like. I'll go over there to G. No bridges attached to G at the moment, so let me come back up here to this vertex. And there are no bridges, oh, sorry, there is a bridge attached to H. This one right here is a bridge, so I don't want to cross that. So let me choose one of these other ones. Go over to B. And B has only a bridge attached to it. And so I cross that, and then I erase B from the discussion. So that brings me over to C. C has one bridge. I'm going to avoid that and cross one of the others. How about come over here to G. And now G only has a bridge attached, so I erase it and I erase G, bringing me down to D. D has a bridge over here and two non-bridges, so I'll choose one of the non-bridges. Over to F. And you can see now it's just going to be a sequence of crossing bridges and burning the vertex attached, so I can finish out the circuit. Okay, so here's my Euler circuit for this graph. Let me erase the process there. Okay, and I can sort of use the letters to visualize going through the circuit now. So I start at A, I go over to B, then I, then F, then G, then H, then B, C, G, D, F, E, D, C, H, I, A. There you go. There's your Euler circuit through the graph. Let's see, how about this one here? Let me check the degrees of the vertices really quickly. They all appear to be even, right? Let's see if we can get a quick Euler circuit through this. I found one without trying too hard. But I could go through the algorithm carefully, right? But that did it. I went through all the vertices of the graph, all the edges of the graph, without repeating any edges.